Welcome students, this is second lecture of Principle of Mathematical Induction. In this, we are going to solve few more questions. So we were taking problems from exercise 4.1. In last lecture, we had solved quite a lot problems. There are a few more problems to be taken. So let's begin with, see, the question was prove by method of induction. Prove by method of induction for all n natural 1 upon 3 into 5. This is not 3.5. This is 3 into 5. What are we doing? We are proving this. 1 upon 3 into 5. 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9. You check this. 3 into 5, 5 into 7, 7. There is a pattern. And so on to n terms. The nth term is not given. If we keep adding terms like this till nth term, the total sum would be n upon 3 into 2n plus 3. This would be the sum. So this is a proposition. This is a proposition that we want to prove. So this is my proposition. I want to prove this. Okay. Now in this, what is missing for me? See, on the left hand side of this proposition, I notice that nth term is not there. So my first, before I go for proving this by method of induction, the first thing that I would be doing is I shall be finding out the nth term. I want to find the nth term of this LHS. Okay. Now in order to get the nth term, what I did, see, you can check here. First, I assumed this to be P of n. What I wanted to prove, that whole thing I assumed it as P of n, that is proposition involving natural number n, where n is a natural number. So this whole thing is P of n, and then this is my LHS of P of n, and this is RHS. For the LHS, I wrote 3, 5, 7. See, I'm writing this 3, 5, 7 are in AP, with the first term A being 3 and the common difference being 2. So if 3, 5, 7, so on it goes. So the nth term, the first factor here, 1 upon, and then this first factor. See, there are two factors. There are two factors in every term denominator. So there would be two factors even in the denominator of nth term. The first one would be the first factor of the nth term. So that way I got it to be 2n plus 1. So the nth term here for this AP would be 2n plus 1. And then I noticed that in every term, in every single term, the second factor is 2 more than the first factor. See, 5 is 3 plus 2. This is 5 plus 2. Now here 9. 9 is 7 plus 2. So even in the last term, the second factor would be this plus 2. Now here I have 2n plus 1 as I found it. So this would be 2n plus 3. So I did it directly. If you want, you can for the second factor, you can proceed as we proceeded for the first factor. Okay, so you can do the way you want. Next, what we did was, after that, see, after that, here, now in the next page, so the LHS of series will have the nth term as 1 upon 2n plus 1 into 2n plus 3, and then I substitute this nth term and the proposition P of n, which is actually to be proved, it becomes like this. Okay, so in this question, since this nth term was not given, I had to work for this nth term, and now we can proceed. So the principle of mathematical induction will start from here. Okay, so now we are going to have the principle of mathematical induction. The step 1. What is step 1 here? Step 1 is, I'll write, we will prove that P of n is true for n equals to 1. That is to prove that P of 1 is true. Okay. Now see, what does that mean? If I have to prove P of 1 is true, what does that mean? That is to prove that now the proposition that you have in this, you will put n as 1. So P of 1, which is now see, you're putting n as 1 on the left hand side. Okay. Now n1 means first term. So you will have 1 upon, you can check 1 upon 2 into 1 plus 2, 2 into 1 plus 2, that is 1 upon 3 into 2 into 1 plus 3, that is 1 upon 5, equals to, on the right you have 1 upon 3 into 5. See, 3 into 5. This is what your RHS will be when you put n as 1. Okay. So what am I getting? What I need to prove? I need to prove that 1 upon 3 into 5 is equal to 1 upon 3 into 5. Now, which is obviously true. You understand? So we have proved that P of n is true for n equals to 1. So here I will write, see, this is what I had to prove. But when I actually see this, I notice that it is true. Okay. Which is, I see that there is no requirement to be proved, because as such, these two are equal. Left hand side and right hand side are equal. So here I write, which is obviously true. Therefore, P of n is true for n equals to, it is true for n equals to 1. Next, now we go for step 2. In step 2, you all know what we will do. See, in step 2, now we begin with step 2. Step 2. Step 2, we start with an assumption. What is that? We will assume that this P of n, which we have here, this P of n which we have here, it is true for n equals to k, where k is a natural number. We will assume that P of n is true for n equals to k. And using that assumption, we will prove. So see, first you assume, then you use the assumption to prove, okay, that P of n is true for n equals to k plus 1. So we have here, I write, step 2, we will assume that P of n is true for n equals to k. N equals to k. That is P of k is true. That is, now see, if P of k is true, what is true? P of k, which is 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 plus so on. And here what you have, 1 upon, see, you put here nsk, 1 upon 2k plus 1 into 2k plus 3, 1 upon 2k plus 1 into 2k plus 3 equals to what you have? You have k upon 3 times 2k plus 3, k upon 3 times 2k plus 3. And see, as per your assumption, this is true. So you write, okay, that is, this is true, your assumption. So this is 1, and remember, this is true. This is what your assumption is. So the next I write, using the above assumption. So next step, using the above assumption, we will prove that P of n is true for n equals to k plus 1. That is to prove that p of k plus 1 is true. To prove that p of k plus 1 is true. That is to prove that. Now see, the proposition you have in this, you will put n as k plus 1. Now remember, if you are putting n as k plus 1, so here you will have n as k plus 1. Okay, just before that n would be k. So what will that series be in such a case? So that is to prove that 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 plus 1 upon 7 into 9 plus 1 upon 9 into 11 and so on and so on and so on. You understand? And what is that nth term? Nth term you are writing is k plus 1. So that is 2 into k plus 1 in one bracket, and then 2 into k plus 1 plus 3 in the other bracket equals to, you see this, equals to, and what would be the RHS? See, even the RHS n is k plus 1. So you have k plus 1 upon 3 into 2 times 3 into 2 times k plus 1 plus 3. You see this? This is what you have to prove. This is what you have to prove. This is your RHS. So now what I notice is on the left hand side, see, on the left hand side, the last term you have is this. Okay, so what would be the a term before this term? What would be the term before this term? See, that would be in place of k plus 1, it would be k. Just one term before, it would be k. So if I write a term before this term, it is 2k plus 1 into 2k plus 3. Okay, so this is to be proved. So I begin with my, so this is what I have to prove. So I have to prove here LHS equals to RHS. See, I have to prove that this LHS is equal to RHS. Okay, and this I need to prove under the assumption that this is true. Okay, this is true. Using this I will prove this. Once again, I may use this I would be using and proving LHS equal to RHS here. So let's begin. I begin with the left hand side. What is left hand side? So here I write LHS is equal to 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 plus dot 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 plus 1 upon 2k plus 1 into 2k plus 3. Okay, 2k plus 3 and plus 1 upon 2k plus 1 plus 1 into 2k plus 1 plus 3. This is my LHS. What will I do now? See, students, look at this part. This part, you know that this part, as per your assumption, is this. You see this? You have the same thing on the LHS there. You have this thing only. You can check. You have the same thing there. So what is this equal to? I will use here for this, I will use the RHS. I'll write k by 3 into 2k plus 3. So here for this I write k upon 3. I write here k upon 3 into 2k plus 3. And here you have 1 upon, when you multiply this inside, so you get 2k plus 2 plus 1, that is 2k plus 3. And here you have 2k plus 5. you have 2k plus 5. The second bracket will become now. From this, I take 1 upon 2k plus 3 as a common bracket, and inside I get k by 3 plus 1 upon 2k plus 5. Okay, so this will be 1 upon 2k plus 3, and I take the LCM. The LCM is 3 times 2k plus 5. Okay, so this will become 2k square plus 5k, 2k square plus 5k plus 3. Okay, so we need to factorize the numerator. The numerator, we are getting a quadratic expression. So here I will write, so 1 upon 2k plus 3, 1 upon 2k plus 3, and here, see, this 2k square plus 5k plus 3 can be written as 2k square plus 2k plus 3k plus 3. Okay, 5k can be written as 5k can be written as 2k plus 3k, and 3 into 2k plus 5 I have. So I get this as 1 upon, I get here 1 upon 2k plus 3, and taking the common, 2k is common, so you get k plus 1, and then 3 is common, so again you get k plus 1, and here you have 3 into 2k plus 5. Okay, so 1 upon 2k plus 3, this is k plus 1 is common, so, and 2k plus 3 upon 3 into 2k plus 5. So 2k plus 3 cancels. We get here k plus 1 upon, what do we get here? We get here k plus 1 upon 3 into 2k plus 5. We are getting this as RHS. Okay. K plus 1 upon 3 into 2k plus 5. This is RHS. We are getting this as LHS. When we solve, we are getting LHS as this. Now let us check what our RHS is. See, because we have to prove that this LHS is equal to this thing. So we have solved LHS, and for LHS we ended up with this part. Let us see what is there for RHS. So RHS is, see, RHS we have, you can check what it was, k plus 1 upon 3 times, we had here, I'll use another color, k plus 1 upon 3 times, inside the bracket, 2 into k plus 1 plus 3. Okay, so this is k plus 1, and when you multiply this inside, 2k plus 2 plus 3, so 2k plus 5, so you have 3 into 2k plus 5. See, we are getting RHS same as what we got for LHS. What does that mean? That means that LHS and RHS are equal. So I'll write here, therefore LHS equals to RHS. What does that mean? It means we have proved that this equals to this. It means we have proved what we have proved. We have proved if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. Okay, very essential part of the principle of mathematical induction, that is step 2. So what we have proved here, students, hence so we can write, therefore we have proved that if see, the second step always starts with if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. Okay, now what does that mean? It means that hence Hence, by principle, by principle of mathematical induction, mathematical induction, we can say that we can say that the given P of n, the given proposition P of n is true, for all n natural. Okay, I hope you must have followed this. You can see, you can watch the whole thing once again, the whole solution. So now the next question is question number 11. To prove that 2 raised to 4n minus 1, 2 raised to 4n minus 1 is divisible by 15, for all n natural by using principle of mathematical induction. So this time, what I have to prove? I have to prove 2 raised to 4n minus 1 is divisible by 15. This is a different type of question to be proved by mathematical induction. Till now, whatever you had to prove, the proposition had a series on left hand side. There was a series on left hand side, and on the right hand side you had an expression which was the sum of the series on the left hand side. But now in this we do not have anything like that. It is a different kind of question. So see, how do I proceed? I understand that if I want to solve any such question, it is required for me to begin with a P of n, So here I write, to prove that 2 raised to 4n minus 1 is divisible by 15, that is to prove that 2 raised to 4n minus 1 upon 15 is a natural number, See, if 2 raised to 4n minus 1 would be divisible by 15, then only you will always get a natural number. Okay, that is 2 raised to n minus 1, 2 raised to 4n minus 1 should be a multiple of 15. This has to be multiple of 15. Okay, suppose I write here 45. So 45 is divisible by 15. Why? Because 45 is 15 into 3. 45 is a multiple of 15. Okay, it is 3 multiple of 15. Okay, so 15 into 3 upon 15, what do you get? You get 3, which is a natural number. 60 is divisible by 15 because 60 is 4 multiple of 15. You understand, this is a multiple of 15. It is 4 multiple of 15. So when you divide, 15 cancels, you get equal to 4. So the same thing I'm writing, 2 raised to 4n minus 1 would be divisible by 15 if 2 raised to 4n minus 1 is a multiple of 15. It is a multiple of 15. Okay. So if it is a multiple of 15, that is 2 raised to 4n minus 1 upon 15 is a natural number. If it is divisible, then every single time I divide this by 15, what I should get? I should get a natural number. Okay. So the next step I write, that is to prove that 2 raised to 4n minus 1 upon 15 equals to m, where m belongs to set of natural number. So now this is my P of n. I assume this to be Pn. This is my Pn. Okay. So I write let Pn be 2 raised to 4n minus 1 upon 15 equals to n. So I will now, this is my Pn and the solution begins from here. So what is the first step? Now you will begin with your first step. The first step, as usual, you will prove that P of n is true for n equals to 1. So I will begin with my first step. I'll begin with my first step. So here I write to prove step 1. This is my step 1. We will prove that P of n is true for n equals to 1. That is to prove that P of 1 is true. That is to prove that P of 1 is true. What is proof? That is, what is P of 1? That is to prove that P of 1 is, which is 2 raised to 4 into 1, 4 into 1 minus 1 upon 15 is equal to m, where m is an integer. Remember, m, okay, equals to m, where m is an integer. M belongs to n is true. This is, we have to prove. Okay, that is to prove that P of 1, which is see, 2 raised to 4 is 16, 16 minus 1 is 15, 15 upon 15 equals to m, m natural is true. This we have to prove. Okay, that is to prove that slightly tricky solution. That is to prove that P of 1, which is 1, see, 15 upon 15 will be 1, equals to m, where m is natural, where m is a natural number, is true. But now check this out, students. When you are getting m as 1, isn't that m value natural? Yes, m is natural. So what does that mean? That what we had to prove, it is actually true. It is proved. So here I will write, see, we had to get, when we put n as 1, we should be getting a natural number. And what did we get? When we put n as 1, we got the answer as 1, and that 1 is a natural number. So I will write which is obviously true. Therefore P of 1, therefore P of n is true for n equals to 1. Okay, so the next will be step 2. In step 2, as you know, the step 2 of principle of mathematical induction begins with an assumption. So here I will write, we will assume that P of n is true for n equals to k. P of n is true for n equals to k. That is P of, see, what was P of n? Here is P of n, right? So that is P of k, which is equal to 2 raised to 4k minus 1 upon 15 equals to or natural number. See, okay, equals to, see here in P of n, what we have m, And what M stands for? M stands for a natural number. Now, when I say P of k is true, what I mean is 2 raised to 4k minus 1 upon 15 would also give me a natural number. This would also give me a natural number. So what I do is I take that as say some other letter I use, and I use say H. Okay, so 2 raised to 4k minus 1 upon 15 is H, where H belongs to n, where H is nothing but a natural number, where H is a natural number, and this is true. This is true, and this is my one statement number one. It is. So now I have P of k. This is my assumption that 2 raised to 4k minus 1 upon 15 is 2 raised to 4k minus 1 upon 15 equals to H, where H is a natural number, is true. Okay, so I'll write here that is okay. Now what? Using above assumption, the next step, using above assumption, we will prove that using above assumption, we will prove that P of n is true for n equals to k plus 1. Okay, that is to prove that I use another color to distinguish. That is to prove that P of k plus 1, which is P of k plus 1, which is 2 raised to 4 times k plus 1 minus 1 upon 15 will also be a natural number. This is what I have to prove. Okay, this will also be a natural number. Okay, to prove that equal to M, where M is a natural number, right? So see, how do I proceed? So in order to proceed, I'll take LHS. This is my LHS. I will work on LHS. And what is my aim? My aim is to end up with a natural number. So I will begin with my LHS. So what is LHS? LHS here is 2 raised to 4, multiply that 4 inside. So 2 raised to 4k plus 4 minus 1 upon 15, which is 2 raised to 4k into 2 raised to 4 minus 1 upon 15. Okay, now see, from 1, look at this. I want you all to see this part from 1. See, what am I going to do? Is this true? Yes, this is our assumption. This is true. Okay, and using this, we are going to prove that this would also be true. So That means we can use this part. Now I want you all to focus on this. See here what I have. I have 2 raised to 4k minus 1 upon 15 as h. So what would be 2 raised to 4k minus 1 equal to? It would be 15h, and therefore 2 raised to 4k would be 15h plus 1, right? So where I have 2 raised to 4k, I can write 15h plus 1. So this I am going to replace by 15h plus 1. Okay, so my LHS now becomes, my LHS will become, therefore LHS equals to, which I am working on, what it will be? It will be 15h plus 1, 15h plus 1 into 2 raised to 4, 15h plus 1 into 2 raised to 4, which is 16, minus 1 upon 15, minus 1 upon 15. That is 15h into 16 plus 16 minus 1. I multiply this 16 inside in both the terms. So here I have minus 1 upon 15. So this gives me 15h into 16 minus 15. 16 minus 1 is 15 upon 15. Now in the numerator, let me take 15 common. So 15 is common. So you get 16h minus 1 upon 15. Okay, so what happens next? This 15 and 15 cancels, and see what am I left with? I am now left with 16h. I'm left with 16h minus 1. Now tell me, what is the h? What is h? H is a natural number. See, look at this. Look at this. What have you written? You have written here already where h is a natural number. See here, you have already written here that h is a natural number. Okay, so here I have 16 multiplied by a natural number. You check this, 16 multiplied by a natural number minus 1. Now tell me, 16, which is a natural number when multiplies a natural number, what do you get? You get a natural number. So when two natural numbers multiply, you end up with a natural number minus 1. Now a natural number, when you subtract 1, finally what you are left with, you are left again with a natural number. Okay, so what I finally understand, that this 16h minus 1 is a natural number. It's a natural number. So here I write, which is equal to a natural number. Okay, which is equal to or natural number, which is equal to RHS, because RHS, what we needed M, that was a natural number. We needed M, nothing but a natural number. So what we can say, therefore we can say that when P of N is true for n equals to K, then okay, you can replace this when by if. That sounds much better. If P of N is true for n equals to K, then P of N is true for n equals to K plus 1. Okay. Now from here starts the method of succession. Okay, that is method of induction. So I write therefore by principle of mathematical induction, therefore by principle of mathematical induction, we can say that P of N, we can say that the given proposition P of n is true for all n natural. That is P of n, that is 2 raised to 4n minus 1 upon 15. 2 raised to 4n minus 1 is divisible by 15. That completes the proof. You can watch this again and practice on your own. Okay, excuse me, students, my apology. This 16 minus 1 is plus 15. Okay, 16 minus 1 is plus 15. So when you take 15 common, it is plus 1. And here also plus 1. But then in totality, the solution will remain same, because if h is a natural, so 16 times a natural number will be a natural number, and when you add 1 to a natural number, that still be a natural number. So the solution is still the same. So I committed a mistake here. I'm sorry for that. 16 minus 1, here it should be plus 15.